Welcome. The title of today's notes worksheet is Complex Numbers Day 1. We'll take some time today developing the concept behind complex numbers and then really primarily focus on just the operations and manipulations of complex numbers. So let's start it out with a couple investigations that you see at the top of your page here, and just definitely kind of see where that leads us. So investigation 1, it just says draw a flowchart representing the relationships of various types of numbers. And it does say leave a little room at the top there, and there's a reason for that, of course. So don't put everything in right here just yet. Let's go a little bit below. And I guess really our discussion should start with the set of real numbers. So if you don't mind, just right about there, kind of that tier down, that would be fine. And as we all know, the set of real numbers can be broken up into two different subsets. So give me two branches off there. And real numbers are based on a set of rational numbers and irrational numbers. Okay, so those two sets combined make up all of the real numbers. And if you could throw that into the mix, that would be great. Now what I'm going to do is just continue on with this branch a little bit. This goes a little further, just different subsets of rational numbers. I have what we would call integers, and then whole numbers. So integers would be essentially -1, -2, -3, 0, 1, 2, 3, etc., etc. And whole numbers would just be limited to 0, 1, 2, and 3, just FYI on this. And then really kind of the last one down here we would, I guess, call counting numbers. Counting numbers, instead of starting at 0, we would kind of count at 1. And each one down below here is a subset of the one above it. All counting numbers are whole numbers, all whole numbers are integers, and all of these, of course, are rational. Just kind of getting that piece taken care of. All right, good. Just a little flowchart representing different types of numbers and where they fit in. Now, everyone, let's move on to the investigation number 2. What I'm looking for here is what type of number is needed to represent the solution set of each equation. So not just what is the solution, but what type of number is the solution set. So if you look at this one right here, nice conditional equation, 2x equals 1, and I kind of look at all these categories. Are there any counting numbers that would make this equation true? 1, 2, 3, 4? No. Any whole numbers? 0, 1, 2, 3, 4? No. Any integers? Any maybe -1, -2? No, absolutely not. So these categories right here are not sufficient for solving an equation like this. So we need something above it. We need a rational number. We need that 1/2, which happens to be, again, a fraction, which, of course, is a rational number. That's it. That's the type of number needed in order to make that equation true. Perfect. All right, so now we come over here. X squared equals 2. You, of course, guys, would undo the square right here. You would square root both sides. Undoing the square, you would actually take the plus or minus, but essentially you would get the square root of 2. And so you'd get the positive root 2, you'd get the negative of the root 2. Now look at the categories here. Any of these kind of fit that solution set? Is root 2, is there any rational number that really makes that equation true? No, and so when we solve, we definitely see that a different type of number is needed in order to represent that solution set. And in this case, rational numbers are not satisfactory. We would need an irrational number, of course. So in order to solve this type of equation right here, we need a different type of number than this set of branches. We need this. Okay, let's get this last one taken care of. Now what happens when I come over here? Look at all these numbers. Is there any rational number that you can think of that would be squared and give you -1? Is there any irrational number that you can square that would give you -1? And as a result, guys, is there any real number that you can square that would give you -1? No. And so what we have is a situation where this entire number set right here is not satisfactory for solving an equation like that. So we need a different type of number that would allow us to do that. And this, what is going to be used today, is an extension of the real number system to the imaginary number system. And so we need an imaginary number to pull that off. And so the way it's going to sort of look just up here, by the way, and you can kind of see the title of the notes, and I don't know if I left myself enough room, everything is really going to fit under the umbrella of a complex number. So all real numbers are complex numbers, and all imaginary numbers are going to be complex numbers as well. Okay, hope everyone's okay with that piece. And so what we need is this, sort of a new formulation of numbers in order to satisfy the requirements for that equation right here. And so now we have a more complete picture of the variety of numbers for these types of situations. All right, very cool. Looks nice. Let's keep it moving along here, and just a quick definition and so forth. All imaginary numbers are going to be based on the foundation of what's called the imaginary unit, and that imaginary unit is going to be denoted by I. And so now I allows us to evaluate the square root of a negative, and you'll definitely see this more on tomorrow's notes worksheet. So I is defined, and let's box this up, everyone. So I is defined as the square root of -1. Absolutely. So now, again, once we have that piece in place, we can solve equations of this sort right here. Perfect. All right, and there's just right below it says which means, and the only reason I want to put this in place is we're going to see it so often in this lesson. If I is equal to the square root of -1, what I would ask you is, what is I squared equal to then? And here's what's kind of fascinating about the connections with these numbers already. You can see that the imaginary unit is already tied to the real number system just by squaring it. So if I square both sides here, obviously squaring this just produces -1. So keep that in mind if you would. We're going to utilize this piece. I is the square root of -1, and that's how we're going to see it. And then I squared is back in the real number system as -1. Okay. So complex numbers would be the number system that results from introducing that number I. And we're going to be primarily working with the standard form of a complex number, sort of called the rectangular form. And it would be A plus BI. When you get to pre-calc, you'll see a different way to represent complex numbers that actually requires a little trigonometry. Kind of cool stuff there. But for right now, A plus BI is what we're going to work on. And that complex number is really made up of, as you can see, two parts. So A represents officially the real part. B is considered the imaginary part. And I, of course, is the imaginary unit. All right. And so just a couple quick questions based on this piece. What type of number do we get when B is 0? Well, when B is 0, obviously this just sort of goes away, and we're just left with this piece right here, which, of course, as we said, is just the real part. So we end up getting just a real number. Now, you would never think about it in these terms, or haven't thought about it in these terms. But, if I gave you the number 3, officially as a complex number, it is really 3 plus 0i. That is as a complex number in all its glory. It has the real part and the imaginary part. Obviously, for our purposes, we've never really expressed it that way, and we don't need to. But again, when you actually see this in pre-calc, it's actually relevant to express it that way. But regardless, so I hope everyone is in agreement that if B is 0, this kind of goes away. You just get your nice old-fashioned real number. No big deal. If B is not 0, you get what we would call an imaginary number. That's how it would be stated. But let's go a little further on this. Let's get a little more specific. What type of number do we get when A is 0? So when this goes away, we're just left with this piece. Obviously, it's imaginary. It goes a little further. We would call it a pure imaginary number. So one more time. If B is 0, we get a real number. If B is not 0, and you kind of have both pieces, it's an imaginary number. It can be expressed differently, but we would call it an imaginary number. But officially, when A is 0, then it becomes a pure imaginary number. You're just focused on this piece right here. All right, great. Now let's go perform our operations on it. So we're going to do 5 operations today. The good news is we can knock out the first 2 really fast. The others are going to take a little more exploration, so let's see what we can do. So adding and subtracting complex numbers, what it comes down to basically, let me just put my 2 cents right here, is we're just going to combine like terms. We combine real parts, we combine imaginary parts. Don't think twice about it. And so in this case, I have two imaginary numbers. That's how I would say it, or really two complex numbers that are not real, because we have this value right here. But regardless, I just combine the real parts. So I have 8 minus 10, and so 8 minus 10 is the negative 2. And I have a 4i minus a negative 2i. And again, just that would give us the imaginary part as a 6 with the imaginary unit I. So again, just combining like terms, that's all it is. If you keep that in mind, shouldn't be a big deal. If you come over to letter B, here is a pure imaginary number. And in addition to an imaginary number, or really just, again, as I said, a complex number that's not real. And let's combine. Officially, this is 0 plus 4i. So, 0 plus negative 3. There we go. And just over here as well, I've got a 4i plus negative 9i. And so how about negative 5i? And there you go. So not really too bad there, just working with adding and subtracting. Combine the real parts, combine the imaginary parts. When you get to pre-calc, you probably see these a little more in a visual fashion, and you can kind of play around with this a little bit. But for right now, just the algebra works out pretty clean. Okay, let's go get the third operation then, multiplying complex numbers. So really, even though this is the same thing, I'm going to express it two different ways. Either we're going to distribute officially or FOIL. And FOIL really is distributing, so really it's the same thing. And so here's what I have. Go ahead and go right into example 2. And we're going to need to be a little careful on this piece. And I actually might work down here a little bit if I get the opportunity. You can work wherever you'd like. But essentially I have this pure imaginary number times this imaginary number right here. And so what I'm going to do is distribute that pure imaginary number in. Something like that right there would do. And so as you can see, guys, I'm getting a negative 15i on that end. And then how about a negative 3i squared? Something along those lines, and I hope everyone sees that piece. Now the question, of course, is, are we done? Now I will tell you that all of our operations that we can do should produce a complex number in that beautiful form, a plus bi. So look for this. Shoot for this, everybody. That's the goal. So as I have this piece right here, does this look like an a plus bi? Well, no, not yet. But what do you notice? And this is obviously the reason I had you tuck it in on your paper up above. What is I squared, everybody? Well, remember, I squared reverts right back into the real number system as negative 1. And so now you can see this piece right here is what gives us the real part of our product. Negative 3 times negative 1 is positive 3. And then the imaginary part with the imaginary unit, 3 minus 15i. And there it is. So a plus bi, that's your goal. Notice here, not there yet. There's our answer. All right, let's go get this one. Here we have two imaginary numbers multiplied together, a little more comprehensive in nature, and so it's time to FOIL. So let's go ahead and just do this quickly in terms of getting those 4 pieces, and then we'll go ahead and interpret. 2 times 3, 2 times negative 4i, 5i times 3, and here's the key. The last should be a negative 20i squared, 5i times negative 4i. All right, so now here's the key, of course. That's the piece. We would obviously put things together. I'm going to take one more step before doing that. If you can do this quicker than I can, that's perfectly fine, of course. But I'm thinking this right here, here's your negative 1. Negative 1 times negative 20 is 20. And now, combine the reals together, 6 and 20. Combine the imaginaries together. Oops. And wasn't thinking there for a sec. Let's clean that up. And so how does 7i sound? Good. So multiplying, just kind of work with that I squared, and you should be fine. Again, looks pretty good. 3 operations in the books. Let's take our time developing the last couple here. So before we can talk about the 4th operation, we're going to talk about something called conjugates. Potentially have seen this before and worked with it in a slightly different context. Just a different way to pursue, I guess. But what we're going to do is utilize this concept of a conjugate to perform a little algebraic trick. So here's what I have. This z, by the way, is just a way to represent that we're talking about complex numbers. So z is equal to our a plus bi. There it is. So there's our complex number. Then very simply, the conjugate of that complex number. Here's the notation for it. This just means the bar above means conjugate. Here again, we're talking about the conjugate of our complex number. And this is what it would look like. So let's box that part up. So there is the conjugate of a plus bi. It's a minus bi. And if it doesn't catch your eye just algebraically, let's just be verbal about it. Basically, a conjugate of a complex number means it's the same real part and opposite imaginary part. All right, and so why are we going to find that? Well, we'll see in just a couple minutes here. Why don't we take about just literally 30 seconds, not anymore. Example 3. Just find the conjugate of a, b, and c. So while I ramble for a sec, make it happen. So the conjugate of 4 plus I would be 4 minus I. There you go. So same real part, opposite imaginary part. Conjugate of this would be negative 3. How about plus 2i? And conjugate of this officially, when it's a pure imaginary number, we probably won't play around with the conjugate too much, but officially the conjugate would be 4i. All right, that's it. That's all I need you to do. But now, let's come back, and I need you to think a little bit more deep and read the question. It says, what type of number is produced when multiplying two conjugates together? So if you need to be concrete about this, create a couple conjugates and FOIL them. But I would ask you, what happens when you multiply two conjugates together? Just like that. There's the complex number, there's its conjugate. What occurs? Well, you would FOIL, and you'd get a real number here. And look at the outside and inside. The part that has created the imaginary part to our complex number, look at their relationship outside and inside. And what do you notice? Well, here's a negative ABI. Here's a positive ABI. Don't they cancel? And so the part that would create the imaginary part to our complex number cancels out. And as a result, we are left with a real number. Let's see if we can go one step further. Let's be specific algebraically. What would that number look like using A and B? Well, as I alluded to, we would do A times A, everybody. A times A is A squared. Outside and inside cancel. So there's the imaginary part. But what happens on the end? We get negative, positive times negative, so we get negative B squared I squared. I squared is negative 1, everybody. So instead of saying negative B squared I squared, I'm going to erase this momentarily. What would that translate to, everybody? Negative B squared I squared. I squared is just negative 1. So doesn't that change that? And we should get this piece right here. And so as you can see, if you know A and B, and you're going to momentarily, we can get that multiplication pretty quick. All right, well, let's move forward then. So the fourth operation, two things tied together, reciprocals and obviously division. And so here's what I'm going to write in. Rather than performing the algorithm as you've seen before with, like, say, polynomials, what we're going to do is come at it from a different perspective. We're going to basically eliminate the I in the denominator and write the number in standard form. So eliminate the I in the denominator, and we're going to do this using a couple tricks. So the idea, of course, is this. We're going to use I for a pure imaginary number, and again, bear with it. You'll see this in action momentarily. For a pure imaginary number, and the conjugate really for a more comprehensive complex number. So would really just be for just a regular imaginary number. I'm going to do it just, I want to make the distinction for you a little better. So I for a pure imaginary number, conjugate for an imaginary number, but I'm going to say as a more comprehensive complex number. Just so we can really make the distinction between the two. All right, that's looking good. And you'll see this obviously in action with examples 4 and 5. So if you're like looking at that, not sure what to make of it, give it a moment or two if you would. Well, let's go do example 4. Example 4 states, find the reciprocal of this right here, and of course, write the number in standard form. So as we all know, reciprocals occur when you just flip the number. Now, don't change the signs. A reciprocal is just a flip. Think of this as over 1. That's obviously this number, any whole number, so to speak, can be written over 1. And so I'm just flipping it to create the reciprocal. Do not change the sign. All right, so this is the reciprocal of 2 plus 5i. Obviously, everyone, this is not written in standard form. So what I want to do is, rather than performing some operation, basically saying, how many times does 2 plus 5i divide into 1? Rather than trying to do an algorithm for that particular quotient, what I'm going to do is just change the form of the number. I'm going to eliminate the I down here. And that should satisfy the requirements. So how do we change this to the real number system? Well, as we already explored, I multiply it by its conjugate. And anything I do to the denominator of a fraction, I must do to the numerator. And now the idea is change the form without changing its value. So obviously I'll go through the process right here, but maybe you're working a step ahead of me. I'm going to do the top first. So nice and easy here. 1 times this. Well, 1 times 2 minus 5i is just 2 minus 5i. That shouldn't scare us too much. Now the whole reason for doing this, of course, is for what happens in the denominator. If you multiply those together, you would FOIL, and you would do FOIL. What would happen to the outside and inside? They cancel. And so you end up getting 2 times 2, which is 4, and you get negative 25i squared. Negative 25i squared is really just plus 25. And so as a result, you get 29. And do you remember the little shortcut that I had said before? A squared plus b squared? Well, here's your a and b. 2 squared and 5 squared. 2 squared is 4, 5 squared is 25. 2 squared and 5 squared make 29. Now, if you left it like this, it's not wrong. I would encourage you to go maybe half a step further. I like really seeing that complex number completely simplified in standard form there. So I kind of like that as a common denominator. There's your A, there's your B with the imaginary unit. Again, this is not wrong by any means. I kind of like that piece if you can. Okay, cool. So as you see, this would be this piece. We use the conjugate to kind of get rid of that complex number in the denominator. And now, obviously, you have your A plus BI when all said and done. Great. Let's do the same thing. Now just kind of straight up division. We're looking really for this divisor and this dividend. How many times does 4i divide into 2 minus 3i? But again, we're looking at it from a slightly different perspective. So there's what I'm going to do, and the idea is just to clean out the denominator and put it back into the real number system. And so let's do that. We can do a conjugate here. It would not be wrong by any means. There's just a slightly more efficient manner, and obviously I wrote it above on your sheet here. How do I get rid of the I in this pure imaginary number? Well, rather than multiplying by negative 4i, the negative 4 really doesn't add anything to the mix. It's the I that's going to matter, because when I multiply it by I times I is I squared. And so that's what this means right up here. Now, just have to compensate for the numerator. And so you can see when I just multiply that pure imaginary number by I, it goes right back into being a real number. So in this case, I will do the denominator first. 4i times I is 4i squared. and 4i squared is negative 4. All right, and let's see what happens when we kind of distribute this pure imaginary number in. This is the imaginary unit, by the way. I times 2 is 2i, and then negative 3i squared for that piece right there. Probably can clean this out a little bit more. In fact, I'm going to momentarily. You know, the I squared is negative 1. By now, that should be firing for you. So the real part here is going to be a positive 3, and then plus the 2i, and over 4. Now, if you left it like this, that's over negative 4, sorry. If you leave it like this, that's fine. Certainly not the end of the world by any means. I would like to go a little further myself. So real part would be this piece right here. Does everyone kind of see me circling that? 3 over negative 4, which would be negative 3/4. There's your real part to the complex number. And then here's your b value right here, along with the imaginary unit, 2 over negative 4. And 2 over negative 4 happens to be negative 1/2. So I kind of like that. Again, to me, it's just you can really see the a plus bi. And that, I don't even need to box it up. There's a blank there. Looks good. Okay, so there's division. Very cool. 4 operations in the books at this point. Let's go get the 5th one. Now, you'll probably be dealing with powers of more comprehensive complex numbers next year. For right now, what we're going to do is explore just a pattern that we see with the powers of the imaginary unit. And there is definitely a reason for the way this table is laid out. Let's try to see it work. So here we go. So I to the first, obviously, is I. That was already explored. I squared, we already defined as negative 1. So there are 2 parts. And then if I just use some exponential properties, I could probably come up with any power of the imaginary unit. So I to the third, as you can see, I wrote on your paper here, is just I squared times I to the first. This, obviously, is negative 1. This is just I. So you have negative 1 from here, and I from here. And negative 1 times I hope everybody is in agreement on that, is just negative I. So take a look at that. Make sure you see that piece. I'm just using these 2 definitions right here to get that. How about I to the 4th? I to the 4th is really just I squared times I squared, both of which, guys, are negative 1, right? So you have negative 1 times negative 1, which is 1. And so look at that nice pattern. Look how it goes. I, and then negative 1, and then negative I, and positive 1. Interesting. Now watch what happens over here. And it would actually be great, now that I'm thinking about it, for you to pause the video and try to do 5 through 12 on your own. Then come on back and see how you did. Well, here's what I thought of, and I broke this down a particular way, but you could break it down anyway, and it works. Obviously, this is I to the 5th, and we just said I to the 4th is 1. So you've got 1 times I to the 1st, 1 times I. It's I. 1 times I squared, 1 times negative 1. 1 times negative I. 1 times 1. And notice, it repeats. What happens on the next cycle? Just to move this along, it repeats. And there, guys, is your cycle of 4. If I continued 13th, 14th, 15th, 16th, etc., would it continue on? Yeah, most definitely. And so I'm hoping you see, and please, kind of revisit this if you need, but basically the conclusion here is that the powers of I repeat in cycles of 4. So if I ask you for any power of I, we just need to know where we are in that cycle. And that's what we'll explore. Probably a couple ways to kind of pull this off, but this is sort of the way I do it, is taking that exponent and really just dividing it by 4, because again, it works in cycles of 4, and then just determining the remainder, because a remainder is just a way to think of where we are in the new cycle. And so in this case, if the remainder is 1, then we happen to be 1 more into our cycle. We're on the top row. And if we're on the top row, then it's I. if when we divide our exponent by 4 and the remainder is 2, well, that means we're 2 down in our next cycle. So we're in the second row. And that would be -1. Again, we're just trying to figure out where we would be in that cycle. If the remainder is 3, then that means we are 3 into our new cycle. And there we go. There's 3 into the new cycle, the third row, and that would be -I. And last but not least, if the remainder is 0, really you're 4 down, I suppose. And if you look at the fourth row, aren't all of these numbers evenly divisible by 4? And so as a result, you would be the last down, and it would be 1. So it'd be great to take a moment and just kind of pursue this a little bit, do A through E, and kind of wrap up the 5 operations here today. So here, let's give this one a try. I to the 20th. Now you could probably count this out and kind of figure out where you would be. I kept the first one rather low, but let's at least see the math in action. So what I would do officially is I just take 20 and divide by 4. And 20 divided by 4 is 5. And obviously the remainder is 0. And so as a result, if the remainder is 0, just according to the table, that means that I would be on the 4th row in my cycle of 4. Those are the numbers that are evenly divisible by 4. And I think you kind of realize that. So as a result, I to the 20th is 1. And you could see that obviously just kind of continuing this 13, 14, 15, 16, 17, 18, 19, 20. And bottom row, and so it's 1. Cool. Let's go get the next. 53. I would take 53, that exponent, and divide by 4. And on the calculator, if you do this, you'd get 13.25, which is great. And basically it means it goes in 13 1/4 times. So here, obviously, everyone, is your remainder. So I'm going to put just a little r right there. That 0.25 would be 1 into the new cycle of 4. And so as a result, if we are 1 into our new cycle, then that means I am in that top row. I'm starting my new cycle. I'm 1 down in that top row. And so as a result, you see if the remainder is 1, then we are in the top row, and it's I. And again, if you counted it out there, that's exactly what you would find. Hey, let's go hit the 79. And always feel free to try these on your own and see, fast forward and see if you're getting them. Well, if you did this one, 79 divided by 4 on your calculator, you get 19.75, I believe, which means 19 3/4. So it goes in 19 times and then 3 into the new cycle of 4 left over there. So 3 is the remainder. So we are 3 down into our new cycle. And if we are 3 down, we're in the third row. And there you go, everyone. So remember, I to the third was -I. So that means the remainder of 3, -I. Cool. Letter D, 46 divided by 4. You'd get 11.5. What that means in terms of our division, of course, is 11 2 out of the 4. 2 into our new cycle of 4, so there is your remainder when you see a 0.5, of course, dividing by 4. And so the remainder is 2. 2 into the new cycle is -1. So as you can see, I kind of gave you one of each there just on these positive exponents. Obviously, it doesn't matter how large the number is as long as you do the division there and see what's left over, how far into the cycle. Last one. Good one to end it on. So a negative exponent. Maybe it's been a little while since we've seen negative exponents. How do I treat those? Well, to make it positive, of course, we put it as 1 over. So I to the -27th is, of course, 1 over I to the 27th. Now, obviously, I'm going to play around with this a little more and see what happens. But just FYI, just to expedite this process, if you did the same thing and took 27 divided by 4 to see where you are in your cycle, you happen to be the third one down. So it happens to be -I. Now, I would ask you, would I ever accept an answer with I in the denominator? No, so please go further. this can be cleaned up quite a bit here, so let's get a little practice on it. Now we have an imaginary number in the denominator. We have dealt with that before. Here we go. Look at this. Imaginary number in the denominator. Look how we dealt with it. And so let's deal with it in the exact same fashion. I'm going to multiply by I over I, and let's see what emerges. I get 1 times I, which is I. That wasn't too bad. How about the denominator? What do you get in that denominator when you pull this off? You get negative I times I, which is negative I squared. Let's see if you've got it. Last piece of the puzzle, negative I squared would really be the opposite of negative 1, which is 1. And there you go. So I to the negative 27th is equivalent to I. There happens to be some patterns with the negative exponents too, if you'd like to explore that in a little detail. Just be careful about trying to shortcut it. Make sure you have it down before you do. All right, I think we'll wrap it up at this stage here. First day of complex numbers, really just dealing with the operations behind it. Really 5 that we explored. All right, well, definitely try some of those practice problems, get comfortable with the manipulation, and then you're ready for the day 2.